Okay, let's do a quick overview of potential difference, and this picture will help us better understand what potential difference really is. Let's say we have a negatively charged plate here and a positively charged plate here, and we have these two positive charges located at the same position away from the negative plate. Now, the first charge is it's smaller than the second charge. This is a positive 1 Coulomb charge, this is positive 3. If we were to take this first charge and move it toward the positive plate, well, positive repels from a positive, so as we move it closer, it's going to gain potential energy. And let's say it gains 5 joules of potential energy. Right? If we were to take this 3 Coulomb charge and move it closer, and if we move it to the same distance, it'll gain some energy, and of course the energy gained is proportional to the charge. So if this one gains 5 up here, then the 3 Coulomb charge will gain 15 joules, like that. Now, we've moved it from the same initial place away from the negative plate to the same final position from the positive plate, and potential difference is the ratio of energy gained to the charge. In other words, it's the energy gained per Coulomb of charge. So this charge gained 5 joules per Coulomb because it was only 1 Coulomb big. This gained 15 joules for 3 coulombs, which means it gained 5 joules per Coulomb of charge that it possessed. Right? So the potential difference V is 5 volts. Or in other words, it's 5 joules per Coulomb possessed by each of these test charges. So these two charges here we call those test charges. And they're used to demonstrate how much energy is gained, right? 5 joules or 15 joules. And when we look at the ratio of the energy gained to the charge, we get the voltage, the potential difference. And what we notice is that the voltage is independent of how big the test charge is. Because the voltage for the potential difference for the 1 Coulomb charge is 5 volts. The potential difference for the 3 Coulomb charge was the same, 5 volts. So potential difference doesn't depend on how big the test charge is that's moving. It's a fixed ratio of energy gained per charge. Let's do a quick overview of Ohm's Law. We saw that Ohm's Law says that the current through a conductor is proportional to the voltage across the conductor, and hence the resistance of the conductor is constant. Now this is true over a wide range of applied potential differences, provided that the environmental conditions like temperature remain constant. The thing is, not all conductors are ohmic. They don't all follow Ohm's law. Any conductor that fails to follow Ohm's law is called non-ohmic. What we do is we compare ohmic and non-ohmic behavior using a graph. So the graph that we use to compare ohmic and non-ohmic behavior is an IV graph, which means current on the y-axis, and it's being graphed against potential difference or voltage on the x-axis. The slope of any graph is the y quantity over the x quantity. So here we have the current on the y-axis and the potential difference on the x-axis. And if you think back to the definition of resistance, right, resistance is defined as potential difference divided by current. So current divided by potential difference is 1 over resistance. So the slope of an IV graph, a current voltage graph, that slope equals 1 over the resistance. As we would expect, if we make an IV graph for an ohmic conductor, well, because the resistance is constant, according to Ohm's law, the slope will be constant. Because 1 over a constant gives us a constant. On the other hand, for a non-ohmic conductor, R changes, right? So R changes as the current and the potential difference change. And because R changes, the slope changes. And we see that change here, like that. So on this non-ohmic graph, I'm going to talk a little bit about this graph using the next slide. What we see is that when we increase the current, slope decreases. Right? So as the current gets bigger and bigger and bigger, the y values are getting bigger and bigger and bigger, the current values are getting bigger. And as those current values, the y values, increase, the tangent line is getting less steep, so the slope is getting less steep. So when current increases, slope decreases. But a decreasing slope means we have an increasing resistance, since they're inversely proportional. The conclusion that we can draw is that the graph, when we're drawing this conclusion from the graph, so this is our conclusion. Resistance of a non-ohmic conductor increases as the current through it increases. So if you send more current through a non-ohmic conductor, its resistance increases. And here's why this happens for non-ohmic conductors. If you up the current, then you're increasing the number of electrons bumping into the metal atoms of the conductor. And by sending more electrons through, you're increasing the frequency of collisions between electrons and the metal conductor. So because the metal atoms are being bumped more often, they start vibrating more. And in fact, this explains why the temperature increases, and this is how the electrical potential energy is dissipated by conductors as heat. So if they're vibrating more because they're getting bumped more, well, that causes those atoms, right, when they're vibrating back and forth more, they start bumping into oncoming electrons more frequently, right? So if you imagine you're at a putt-putt course and you're trying to putt the golf ball through the windmill, the hole that's being covered by a rotating windmill, and so you've got these fan blades coming down and blocking the hole, it's going to be a lot easier to pass the golf ball through the hole when the windmill is moving slowly. If you speed up the windmill, right, if it starts moving faster, it's going to be much harder, it's much more likely to bump into your golf ball. So that's the same thing is true for atoms bumping into electrons. Electrons are like the golf ball, trying to pass through, and as the windmill, the atoms move faster, they're more likely to hit the electrons, the golf ball. So if electrons are getting bumped more, then that slows down how fast they move through the wire. And there we are. If they're moving slower through the wire, that means that we have less charge flow and the resistance is increased. Now we can't forget that the slope of an IV graph is inversely proportional to resistance. So that means that as the graph gets steeper, the resistance is decreasing. And as the graph gets less steep, resistance is increasing. Right? Now an example of a non-ohmic conductor is a lamp, which we also might call a filament or a light bulb. And you have to be able to sketch that graph for a lamp, this graph here. Right? And see how as it gets less steep, resistance increases. So be able to sketch that graph. Electrical power is the rate at which electrical potential energy is dissipated, converted, or supplied. Right? So sometimes potential energy is supplied, other times potential energy is being dissipated or used up. So power equals delta PE over delta T. But of course, delta PE is equal to the voltage times the charge, like that. And we could separate out V and put it in front of the fraction, the ratio. And when we do that, what you see is that we have current, Q over T, right? Q over T is current. In other words, if we replace Q over T with I, current, we arrive at this equation, power is equal to voltage times current. And if you replace voltage with I times R, you get power is equal to I squared times R. And then if you come back up here again and you replace I with voltage over R, resistance, then you get this equation. Power is V squared over R. So be able to derive these equations in the way I've shown, starting from this step here. Be able to arrive at this equation, this one, or this one. Now every circuit has, let's say we make a circuit and it has a bunch of different resistors and they're connected in all these different fashions and they make all these complicated pathways. Every circuit can be simplified, right? Because every circuit has an equivalent resistance, which you can think of as a total resistance or a net resistance. So imagine, for every circuit, there is some equivalent resistor, which is the one single resistor that could replace all those resistors in the circuit and still draw the same current from the power source. We call that equivalent resistance. We give it the symbol Req, and it can be calculated from how the individual resistors are set up in the circuit. So whenever you have resistors connected like this, so that they form one pathway for charge to flow, that's called resistors these are in series. We call these a series resistors. So these are series resistors, and that means that there's only one pathway through them for current to flow. On the other hand, we could have parallel resistors, and that's when the resistors provide multiple pathways through which current can flow. So if current comes in here, then it could go up this pathway, or it could take this pathway, or it could go down and take this pathway. There's a junction. Anywhere you see a junction, there's the splitting of paths, and that means that we have things in parallel. So if we have resistors 1, 2, and 3 in series, here's how you calculate the equivalent resistance. When they're in parallel, this is the equation for equivalent resistance. And we can use this for any portion of a circuit in series and any portion of a circuit in parallel. So here's a big, nice chart which summarizes everything we know. Here's what we know about the terminal voltage, which is really just the voltage being supplied by the battery to the circuit. It's the voltage across the terminals. And here's everything we know for a series portion of a circuit, or a series resistors. And here's everything we know for parallel resistors. Notice that the total current is coming through this wire. All the charges pass through R1, right? Then the total current, all of the charges pass through R2, and the total current, all of the charges pass through R3. Here, on the other hand, the total current comes in, it meets this junction. Some of the current goes up and passes through R1, that's called I1. Some of the charges, I2, pass through the second resistor, and then some go down, and some of the charges pass through R3. And then they meet back up again over here. So we have the total again. But in this parallel configuration, the current splits up. Some charges take this top path, some take the middle path, some take the bottom path. In this case, the total voltage dissipated by the three resistors is just V1 plus V2 plus V3. Over here, on the other hand, the voltage dissipated by R1 is equal to the voltage dissipated by R2, and it's equal to the voltage dissipated by R3. Okay? And we can apply Ohm's Law, V equals IR, which is what I've done in these equations here, and in these equations, as well as here and here. And then I've also written in the equivalent resistance equations.